All right, we're starting. We are going to continue with curve sketching, so put your handouts up. We are moving on to example C. It's very similar to example B. And the problem's going to be the same. I'm going to ask you, find the intervals of increasing, decreasing, concavity, maximums, minimums, intercepts, whatever, and sketch the graph. So that's always going to be how the question is going to be phrased. And so now we're going to run through the steps. Always the same 6 steps. Always do that in the same order. So, first step.
Find what?
No, domain. What's the domain? All real numbers, polynomial. Second step, intercepts. So let's talk about the x-intercept. Set y equal to 0, solve for x. Oh.
Factor.
Factor what?
X to the third. X minus 4. Then set 4 equals 0.
Right, so x equals 0,
0 and
x
4.
equals 4. Those guys are my x-intercepts. Y-intercept.
So y 0.
Set x equals 0.
Yeah.
So I get y equals 0 is my y-intercept. Third step, asymptotes. How do I find those?
Yeah.
None. How do we know?
Polynomial.
Polynomial. Don't even have to check. We know that polynomials do not have asymptotes. Moving on. Step 4. Increasing, decreasing, maximum, minimum. How do we find that?
Take the derivative.
Right, we are going to do the first derivative test. So we're going to find the derivative, which is
4x to the third minus 12x.
then
U equal to 0 undefined.
set equal to 0 or undefined, but it's a polynomial, it's never going to be undefined. So I set equal to 0 for the critical points. So I have 4x cubed. So what does that give me?
You factor out
What?
4x squared. Then x minus 3 equals 0.
So x equals 0, x equals 3. And now we are going to test these on a number line in the first derivative. So I'm going to plug in 0, I will plug in 3, and I'm going to test random points in each interval. Give me a number here. Minus 1, 1, 4. Okay, and I'm going to plug those into the derivative. The factored form is usually easier to plug it in. Notice that the first part is a 4x squared. That's always positive, so it's not going to contribute to the sign. So I can only plug it into this part, and I can get away with it. So if I plug in minus 1 here, positive or negative?
Negative.
Negative.
Negative. So decreasing. Plug in 1 here, positive or negative?
Negative.
Negative. Decreasing. Plug in 4 here,
Positive.
positive. Increasing. Can I make any conclusions here?
Yes.
What?
You have a minimum at 3.
3 is a minimum
You have
because I'm decreasing here and increasing there, and I'm continuous at 3. That makes it a minimum. So now conclusions from step 4. I must say where I'm increasing, where I'm decreasing, where I have maximums, where I have minimums. So where am I increasing? Interval.
Were you increasing? Were you extending?
3 to infinity, yeah.
Decreasing.
Negative infinity to. Oh, yeah.
Maximums.
None.
Minimums. 3 comma what? How did I figure out the y value? Plug it back into the original. Whenever I'm looking for a coordinate, a location, I use the original function. So I'm going to put 3 back into the original. So this will give me 3 to the 4th minus 4 times 3 cubed. It's 81 minus 4 times 27.
So
What is that? What is that? 108. Gives me what?
Negative 27. And I don't.
so we're gonna substitute the x value to the original for the minimum always?
Yes, this is the coordinate for the minimum. This is not an interval. This is actually the point I'm going to plot on the graph.
I have a question. For the decreasing, why do we put it to 0? Isn't 0 included? It's a polynomial.
No, at 0, the derivative is 0, so it's not actually decreasing. It's just level.
Oh.
Something else. Now we move on to step 5. Step 5 is where we do concave up, concave down, and inflection points. What do I do here?
Second derivative.
Second derivative, I will do the concavity test, which I introduced at the beginning of last class. So I'm going to find the second derivative, which is
12x squared
derivative of the derivative.
minus 24x.
I set that equal to 0 or undefined. It's never undefined, it's a polynomial, but I set it to 0 for the critical points.
After.
Right? I emphasize things like that because I want you guys to know it's not random. You don't always randomly set a derivative equal to 0. There's a specific reason why I'm setting it to 0. Okay. So now how do I solve this?
After 12x, then x minus 2 equals 0.
So I get x equals 0, x equals 2, and I'm going to test that in the second derivative. Number to plug in here. So plug into the factored form. Negative 1 here gives me a negative. Negative 1 here gives me a negative. Negative times negative is positive. Plug in a 1 here, that's a positive. Plug in a 1 here, that's a negative. Positive times negative is negative. Plug in a 3 here, that's a positive. Plug in a 3 here, that's a positive. Positive times positive is positive. What does positive mean in the second derivative?
Increase.
No.
Concave,
Concave
yeah.
up. So
Yeah.
it means I shape like a smiley face. Negative.
Concave
Concave down, shaped like a frowny face. Positive.
Concave
Concave up, shaped like a smiley face. Any conclusions here?
You have 2 inflections.
I have 2 inflections. At 0, I switch from concave up to concave down, and I'm continuous at 0. This makes it an inflection point. 2, I again switch from negative to positive, so I switch, that makes it an inflection point. You guys remember day 1 when solving this equation? It was like, oh, you do that, guys, and now it's like, yeah, you just factor that out. You said you now you guys are like, whatever. Back in algebra, that was like the hardest thing in the world.
Yeah,
You're like, oh my god, they asked me to find the x-intercept. What do I do? Go to the tutoring center, complain, oh, teacher sucks. He doesn't teach anything. This is so hard. It's crazy. This test looks nothing like what he does on the board. And now it's like, you just do that. Yeah, you do that. You do that. Now you're all just, whatever. Conclusions, concave up, concave down, inflections. Where am I concave up?
Negative infinity to 0, union to the positive infinity.
Concave down.
0 to 2.
Inflection points.
0.
0, comma.
You got
Plug into the original. What was the original? It was y equals x to the 4th minus 4x cubed, right?
Yeah.
So you plug in 0 here, you get 0. The other one is when you plug in a 2. Plug in 2 here, you would get 16. 2 here, you get 8. That's 4 times 8, which is what, minus 16? Those are the conclusions from the step 5. By the way, notice that these things I'm boxing, the problem specifically asks for them, so you do have to indicate when you find them. Right? So if you're specifically asked for where's concave up, concave down inflections, that is a part of your answer. So make sure you box it to indicate, I found it, here's what you wanted. Now, final step, step 6, to actually draw the picture. So at this point in step 6, we're going to summarize everything we knew from the previous 5 steps, and we're going to put it on this picture. That x-axis is sort of whatever. Intercepts.
0.
0 is 1. I know I have to pass you that point, so I'm going to actually plot that point.
And x equals 4.
4. Okay. Now the next step was asymptotes.
No,
There are none.
asymptote.
The next step was increasing.
3 to infinity.
So I'm increasing from 3 to infinity. So what I do is down here I write a very light increasing. Anywhere else?
No.
No, I'm decreasing everywhere else. So I'm decreasing here and decreasing all the way back.
And your minimum?
Maximums and minimums.
No maximum.
3.
3, negative 7.
3, negative 27 is a minimum, so I'm going to plot that point, call that a min, and it comes over here at minus 27. Okay, so that's what the information that step 4 gave me. Move on to step 5. Where's the concavities? Oh, well, I have it here. So from 0 to negative infinity, from here all the way back, I am concave up. I am also concave up from 2
To infinity.
infinity, concave up, and in between, I am concave down. Inflection points, I have 2 of them. 0 is an inflection point, so I'm going to label that INF. 2, comma, minus 16 is an inflection point, so I'm going to label that. And that's also an INF. Right, so that's it. That's all the information I had from the previous 5 steps. So now I literally forget all that, and this is going to be my guide to draw the graph. So you start in each region, and you just do what it tells you to do. These points are points you have to pass through. You must hit those points. Okay. So over here is the biggest region. What am I doing? Decreasing, concave up. So it means I'm decreasing, and I'm shaped like a smiley face while doing that. So I built that. Boom. That's the first step, right? It's dropping as I move from left to right, and I'm shaped like a smiley face while doing that. Then I move into the next section, which is this section here, which is decreasing, concave down. So I'm still moving down, but now I have to switch to a frowny face. And this is an inflection point, so that's another confirmation. So now I switch to a frowny face like that. Now I move to this section between these 2 coordinates. Notice here, I'm still in the decreasing region, but I just moved into the concave up region. So here I'm decreasing and I'm concave up. So now I'm going to switch again to a smiley face. So I'm decreasing this whole time, right? But my concavity is changing in each region. And it's based on where these guys are, right? Now I'm over here. I'm in the last region. I should be increasing, concave up, and I need to pass through that coordinate. So I'm going to move up as I go from left to right and shape like a smiley face. And that is the graph.
I have a question.
Yes?
So since it's decreasing from that side to this side, right? We wouldn't put an arrow in the top.
Yep.
We would.
Yeah, because it actually goes up forever. It doesn't like stop.
This would be like a question on the test. This like how is it written out in the handout?
The what?
So would this be how we written out in the test exactly how it's on the handout?
Yep. In fact, I do recommend you do all these steps. You keep like these headings. It will keep you from getting lost. It also helps you when you're practicing and you write that out all the time. It gets you into a groove. Your brain will run half on autopilot when you're in a test. That's the goal, right? You don't want to give your brain too much reason to start freaking out on you. It's just, you want it to feel comfortable. Oh, I know this. The next step is going to be this. The next step is going to be that. The next step is going to be that. So instead of wasting its time freaking out, it's wasting its time anticipating the next step, right? Which it automatically knows what's coming. Right? It's how your brain likes to work.
That's how it works with the quiz, that it automatically knows it's coming.
Yeah, yes. But you don't freak out when it doesn't show up and stuff. Okay, so any other questions?
How how strict would you be on drawing it? Like it would have to be exactly like
As long as the right behavior is exhibited, I don't really care about your artwork in general, but I will care if it shapes like a smiley face or a frowny face or something like that. But if you can't draw a smooth line in your ground, like, because you're trembling and you do like that, then I'm like, okay, that's kind of, yeah, I see it. You have some leeway, but you need to be, concavity is a very important part. So I need to be able to understand that, yeah, that's kind of an inflection point. You know? Okay, let's do another one. Let's see here. Will be a nice one. Let's try to do G. I'm not going to do every single one. I'd like you guys to try some on your own. A good place that if you want to check it is a website called graph.tk. You type that in and you can type in the formulas. You just type y equals blah, blah, blah. You type out the formula and it'll actually graph it for you and you can compare it to what you actually do. But anyway, let's move on. Y equals x cubed plus 2x squared plus x. So yeah, find all the intercepts, asymptotes, intervals of increasing, decreasing, concavity, maxes, mins, inflection points, and then use that information to sketch the graph. Right. The problem is literally going to be phrased this way. And if you're given the derivatives, I'll say it. But by the way, if it's a polynomial, I'm not going to give you the derivatives. I'll give you the derivative if it's annoying to find the derivative. Okay, step one, domain. Everything works, it's a polynomial. Step two, intercepts. X-intercept. How do I find x-intercept?
set y equals 0.
Set y equal to 0. How do I solve that? Now what?
Factor again.
What is that factor?
X plus 1, x plus 1.
X plus 1 times x plus 1. Right. So we have that. So I get x equals 0 or x equals minus 1. Y-intercept. Plug in x equals 0. Step 3, asymptotes.
No asymptotes.
None. Step 4, increasing, decreasing.
Maximum.
Maximum, minimum. So we're going to do the first derivative test. So we're going to find the first derivative.
3x squared plus 4x plus 1.
And then set a equal to 0 or undefined, never undefined. I do this because I want to find the critical points. So how do I solve that? Right, we'd be foiling, right? The last digit is a 1. There's only one way to get that. It has to be a 1 and a 1 here. This is a 3, right? So it has to be a 3 and a 1, so it's 3x and x. Then you try to figure out the signs. Well, the outside is 3x, the inside is x. Can you get to 4x? You add them, so they both have to be positive. So I get x equals minus 1/3, or x equals minus 1. Then you do the number line. Minus 1 is over here. Minus 1/3. Plug a number over here. Two. Number over here, minus 1, 0. Number between minus 1/3 and minus 1. A half would work.
Yeah.
Minus a half. Right? You could also do something like minus 2/3, right? Because this is 1/3 and one is 3/3, so in between them is 2/3. So there are a couple of ways you could write down that. So now I'm going to take minus 2, I'm going to plug it into here. Plug in minus 2 here, I get a negative. Plug in minus 2 here, I get a negative. Negative times negative is positive. Plug in minus a half here, I get 1.5 plus 1, negative. Minus a half here gives me positive, so overall that's negative. Plug in 0, positive, 0, positive, positive. So I'm increasing, decreasing, increasing. So conclusions, this guy's a maximum, this guy is a minimum. So now conclusions from step 4. Where am I increasing? Where am I decreasing? Where am I a maximum? Where am I a minimum? Negative 1. And then
Negative 1/3 to 0. Oh, infinity.
and then decreasing in between from minus 1 to minus 1/3. Maximum occurs at minus 1 comma something. Minimum will occur at minus 1/3 comma something. So how do I find the values here?
Substitute your original expression.
Substitute into the original. So I'm going to go here, I'm going to plug in minus 1. So I'm going to take minus 1 cubed plus 2 times minus 1 squared plus minus 1. So that's minus 1, that's minus 2, right? Plus 2, that's a 0. And then here, for this one, I'm going to plug in minus 1/3 plus 2 times minus 1/3 squared plus minus 1/3. So this gives me minus 1 over 27 plus 2 over 9 minus 1 over 3. How do I figure that out? Common denominator, right? Which would be 27, right? So this, how do I get this 27? Multiply by 3 over 3. I get plus 6 over 27. This multiply by 9 over 9. I get minus 9 over 27. So I have minus 10 plus 6, so I get minus 4 over 27. That is step 4. Step 5, verifying concave up, concave down, inflections. So we're going to do the concavity test. So we need the second derivative, which is 6x plus 4. I'm going to set that equals 0 or undefined. Happens to never be undefined. Set it here for critical points. So this means x is minus 2/3. So we already have minus 2/3. So I can plug in a number over here like minus 1, plug in a number over here like 0. Plug in minus 1 here, I get minus 6 plus 4, that's negative. Plug in 0 to here, I get plus 4, which is positive. So I know I'm concave down like a frown here. If you're negative, you're feeling down. So positive, concave up, up like a cup, smiling, happy. Makes this an inflection point. Concave up, concave down, my inflection happens at minus 2/3, comma. So again, we're going to plug that into the original. So I'm going to take minus 2/3 cubed plus 2 times minus 2/3 squared plus minus 2/3. So this is going to give me minus 8 over 27. Plus 4 times 2, 8 over 9, minus 2 over 3. Same idea, create the common denominator, so it's minus 8 over 27. Multiply this by 3 over 3, get 24 over 27. Multiply this by 9 over 9, minus 18 over 27. So I have here, what is that, sir?
Minus 26.
Right, that's minus 26 plus
24 is minus 2.
So I get minus 2 over 27. Brings us to step 6. Draw the picture. Now I start to summarize all the information we found so far. Domain is everything intercepts. X-intercepts.
0
0
and -1.
and -1. Okay, the y-intercept was 0. Asymptotes, there were none. Where am I increasing?
From negative infinity to 1.
And then?
And then from negative 1/3 to infinity.
And from negative 1/3
To infinity.
and then I'm decreasing in between. Okay, any maximums, minimums?
Minus 1, 0.
This is a maximum.
And then
Minimums?
minus 4 over 27.
What's the x coordinate? For this one.
Yeah, 1/3.
And then minus 4 over
minus-
27.
Yeah.
So here's a minimum at minus 4 over 27. Okay, that's from step 4. Step 5, concavities. Where am I concave up? Where am I concave up? So from here, call it minus 2/3. And so from that point to infinity, I am concave up. And from that point back, I am concave down. Inflection happens here, and minus 2/27, which is halfway down. That's an inflection at minus 2/27. Okay, so that's all the information. Forget everything else I did. Right now, this is the focus. And here, we're supposed to be increasing, but concave down, because that's the region we're in, the increasing concave down region. So we're moving up as we go from left to right, but I'm shaped like a frowny face, and I must pass through this point, and it's going to be a maximum point, so I'm not going to go above it. So that's that part. Now I'm in this region. I'm decreasing, and I'm still in the concave down region, so I'm going to just go like that. Now I'm in this region, still decreasing, but I'm concave up now, so this is an inflection, so I'm going to switch to a smiley face. Now we're in this guide, which tells me I should be increasing concave up, and I should pass through the 0, so this is going to be tight, but and that's going to be our graph. Questions? So yes, a curve sketching problem is long, but it's the kind of thing that if you get into a groove with, you should be able to just grind one out. If such a problem comes on a test, it will be the only thing you have to do. It's not going to be a problem that has parts with partitions. It's going to be like, give me this and sketch the curve, and that's all you have to do for that problem.
What about?
And it'll be in the second part. In the final, something like this will come in the second part. So you could choose to not do it. But at the same time, it's kind of one of those follow your nose kinds of things. Yes, it's kind of going to be the longest kind of problem we're doing, but it's still like, you know the steps and it's much more intuitive. It's not like related rates where you have to figure stuff out of the blue.
Jhevon,
yeah.
this decreasing concave down is going to come from infinity, from the top. If it's decreasing
Yeah,
concave
well,
down.
it depends on where, but it could be. That would be possible. Yeah.
Okay.
Yeah, that's a possibility. Depends on the group. Let's do an interesting. Let's do problem A from the bottom section. So in this case, I have y equals, the original function is x squared over x squared minus 4. And you're given the derivatives. Y prime is equal to minus 8x over x squared minus 4 squared. The second derivative is 8 times 3x squared plus 4 over x minus 2 minus 4 cubed. And if you're given derivatives, you don't have to prove them, you don't have to verify, just that's the derivative, run with it. Don't waste your time finding the derivative if they're given. Okay, and all the same things apply. We need to find intercepts, asymptotes, increasing, decreasing, max, mins, concavities. Okay, so step 1, domain. What's the domain? How do we find the domain? How do we find the domain of something like this?
The bar just not equal
The
zero.
denominator cannot equal 0. Notice that the denominator also is the difference of squares. This is an x minus 2 times an x plus 2. So what's the domain?
All x except x plus 2 minus 2.
All x except 2 and minus 2. So how would I write that? Negative infinity to negative 2, unit negative 2 to 2, unit 2 to infinity. So everything works except I have to avoid negative 2 and I have to avoid positive 2. So that's my domain. Intercepts. So let's work on the x-intercept. How do I find the x-intercept? Same way we always find it, set y equals 0. Right? Remember, a fraction is equal to 0 when the numerator is equal to 0. So that just means x equals 0. Y-intercept. How do you find the y-intercept? Plug in x equals 0. Same way we always find the y-intercept. So that's 0. Right? Just because it looks scary, the rules do not change. You find it the same way you always find it. For x-intercept, plug in y equals 0, solve for x. For y-intercept, plug in x equals 0, solve for y. 3, asymptotes. Now we're not in the case where there are none. We do have them. Let's talk about horizontal asymptotes. How do we find those? Right, we have to find two limits. The limits as x approaches infinity of the function. So that's x squared over x squared minus 4. And I have to take the limit as x approaches negative infinity of the function. Okay, what's this? It's 1. Highest power on the top and the bottom is the same, so it goes to the ratio of the coefficients. This? No, it's the same idea. So it's still 1. So y equals 1 is a horizontal asymptote. Now look, the vertical asymptotes. How do we find those? Right, set the denominator equal to 0. So you basically get the guys that are in the domain. So you have x equals 2 and x equals minus 2. Those guys are your vertical asymptotes. And again, I'll show you how to put those on the graph. So now we will move to step 4, which I'm going to leave this up. Increasing, decreasing, maximums, minimums. So now I'm going to use the derivative y prime equals 0 or undefined. So now remember, it's a fraction. A fraction is equal to 0 when the top is 0. So that's minus 8x equals 0. And it's undefined when the denominator is 0. So that means x squared minus 4 equals 0. So this means x equals 0 or x equals plus or minus 2. So I have 3 critical points. 0, plus 2, minus 2. I'm going to plug that into the first derivative. Now I can go through and think about it, but we can use some ingenuity here. Notice that the denominator is a square, right? Which means it's always going to give me a positive number, right? So pretty much I can ignore that because it's always going to give me a plus sign. So I'm only plugging into the top. So I can plug in a minus 3, minus 1, a 1, and a 3. And I'm going to plug these into negative 8x. Plug in a negative number for x, I get a positive. Negative number for x, I get a positive. Positive number for x, I get a negative. Positive number for x, I get a negative. So I'm increasing, increasing, decreasing, decreasing. Any conclusions here?
Maximum of 3.
I have a maximum at 0. Anything else? This is nothing, right? And even if this looked like a max or a min, it wouldn't be because it's not in the domain, right? But 0 is in the domain, and I'm increasing on the left, decreasing on the right, so that's actually a maximum. So now let's make our conclusions. Where am I increasing? Where am I decreasing? Where are my maximums? Where are my minimums? Where am I increasing? Negative infinity to negative 2 union negative 2 to 0. I am decreasing from 0 to 2 union 2 to infinity. My maximum is 0, comma 0 by plugging it back into the original. Minimum, there are none. Moving on to step 5. Step 5, we're going to do concave up, concave down, inflection. So here we're going to do the concavity test, second derivative equal to 0 or undefined. So again, the second derivative is a fraction. It's equal to 0 and the numerator is equal to 0. So here I'm going to set 8 times 3x squared plus 4 equals 0. It's undefined if the denominator is equal to 0. So here again I get x squared minus 4 equals 0. What is x here? What do I get for this? Huh? What? Huh? I can divide both sides by 8. The 8 doesn't.
Then you subtract the 4.
Subtract the 4, so I get negative 4. And divided by 3, so I get negative 4 over 3. And I take the square root of minus 4 over 3. That doesn't cause a gut-wrenching feeling to anyone or anything? Is that just me? It's a negative under a radical. It's not in the domain of the radical. There's no solution here. Right? This is never actually 0, right? Because x squared is always 0 or bigger. I'm adding a 4 to it. It's never going to be 0. What about this guy? Y double prime minus 2, positive 2. I'm going to test values here, here, here. Plug in a minus 3 into the second derivative. Okay. So again, now I'm going to look here. Notice at the top, there's a square plus a positive number. The numerator will always be positive. So I'm pretty much going to ignore it and look at the bottom. Right? Now if I plug in a 3 here, what do I get? 9 minus 4 is positive, right? So that's a positive number here. If I plug in a 0, I get minus 4 cubed, which is a negative. If I plug in a 3, I get 9 minus 4 again, which is positive. So positive here means concave up, like a cup. Negative here means down, like a frown. Positive here means up, like a cup. Any conclusions here?
So concave up is from negative infinity to 3.
Up from
Negative infinity to negative 3.
to negative 2. Remember, these are the values. So negative infinity to negative 2.
And then from 2 to infinity.
concave down is in
Minus
between
two.
minus 2 to
And
2.
two.
Any inflections?
-2.
And 2.
No.
Yeah, we have 2 inflections.
We don't have any inflections. Why don't we have inflections?
We do have.
We don't.
No.
2 and -2 are not in the domain. They're nothing. They're not points on the graph. That was the importance of step 1. In step 1, we learned that 2 and -2 I cannot plug in.
Oh, yeah.
They do not exist on the graph. That's why they're not inflections. Right? It's not just a matter of switching concavity. You have to exist at the point. Right? So notice that they are not inflections. None. Right? Because 2 and -2 is not in the domain. So they can't be points on the graph. Right, I can't plug in a 2 or -2 here. I can't get a coordinate.
On the test, we'll get to explain it, or we just do right now?
No. That's why I didn't really box it. That's just for your education. Okay, so now let's actually graph this thing. It's probably going to look weird. Let's see what we have here. Okay, let's go through and put in our information. Domain. Everything except 2 and -2, which means I can put a hole here. -2 I cannot touch. +2 I cannot touch. All right, intercepts. The origin. So I do go through here. That's an intercept. The y-intercept will be the same thing. Asymptotes. Vertical ones. Let's start with those. X equals -2 and x equals +2, right? Now remember, asymptotes, how we represent them on a graph is broken lines. So those were the vertical asymptotes. Do we have horizontal asymptotes?
Y equals 1.
Right. Y equals 1 was a horizontal asymptote, so that's a horizontal line, and it's a broken line. Okay, next step, step 4. Any
Increasing.
critical points? Do I have any maximums, minimums?
Maximum at the origin.
So 0, 0 is a maximum, so that's a maximum point. Do I have any minimums?
No.
No. Increasing, decreasing.
Negative infinity to 2, union negative infinity to 0.
Negative infinity here, I'm increasing. Between here, I'm increasing. And then I'm decreasing everywhere else. Decreasing here. And I'm decreasing there. Okay. So that's step 4. Step 5. Oh, we can't read up here. I'm concave up between 0 and 2, -2. So this here is concave up, CU. And I'm also concave up over here.
From 2 to infinity.
So this is CU. And I'm concave down in between. So I'm concave down,
With no inflection points.
concave down, and no inflection points. So at the moment, not a lot of information to go by. We just have one point and then a bunch of things that we can't do. Like don't cross here, don't cross there. Okay, so let's start. In this region here, what's going on?
Increasing concave up.
Increasing concave up. All right, so how do I do that?
Start from the bottom.
Start from the bottom, now we're here?
Concave.
Okay. So do we start here?
So increase, yeah.
Why can I not start there? The answer is no, I can't start.
No.
Why not?
Negative infinity.
Well, if I'm here and I'm increasing, what's going to happen? Boom, I'm going to cross the x-axis at some point. Should I be crossing the x-axis over here? No, there's only one x-intercept and it's over there. So I cannot start from here. Can I start from here?
So yeah, but you can go with
Okay, well, let's say I start here. What's going to happen?
still
You're gonna cross.
Well, I'm going to do that, which in general is fine. Crossing a horizontal asymptote is not a big deal, right? It's possible, right?
Really?
But the thing is though, when I'm going to negative infinity, I should be leveling off here, right? That's what the limit says. So what would I need to do to level off here if I'm doing that? Well, I obviously need to turn back to level off, right? What will happen? I'd create a minimum. I'd also create a region where I'm decreasing, which I know doesn't happen. So I cannot start from there either. So I must start from up here. And look like that. And then look like that. Right?
this would be a test.
Right? So you can test the regions. Another way to do it is to just take a number here, like a -3, plug it into the original function, you'll get the point is up here. And at that point, you know you can't cross anything else. Right? So there are several ways to do it, but you can just by trial and error just think, okay, can I start here? The answer is no, because I go through the x-axis and I'm not supposed to. Could I start here? The answer is no, because to get back there, I'd have to be a decreasing function, and I'd create a minimum, so I have to start here. Right? So this side of the function looks like that. Now, we're in this region. Where should I start? Should I start here?
No, on top of the horizon.
I can't start here because I have to go down to hit this maximum, and if I'm going down to hit the maximum, it's not a maximum, right? For the same reason I can't start here. I have to be starting from here. I should be increasing and I should be concave down, right? So I'm going to go up, but like a frowny face, and I have to pass through that point.
Why isn't it next
Now,
to the other one?
Remember, I cannot cross this vertical line. Those vertical lines are not in the domain. They're vertical asymptotes. You can never touch a vertical asymptote. Yes?
I don't understand how that point is a max if there's points like above it.
It's a local max.
Oh.
The first derivative test finds local max, not absolute max. Right? So he doesn't have to be the biggest in general. Just in his small world, he's the biggest. Okay? So that gives us that part. Right? This region, I am decreasing concave down. Right? So I'm falling as I move from left to right, and I should shape like a frowny face. Like that. Right? So here I'm increasing concave down, then I decrease concave down. So I'm like a frowny face the whole time, but on this side I'm increasing, that side I'm decreasing. Now here, I should be decreasing concave up. So now the question is, where do I start? Could I start here? The answer is no, because that would create a point where I created this. Same reason here, I can't start here, because I'd have to come back up to level off, which would create a minimum. So by that reason, I have to start here, and I'd be decreasing, leveling off. And then of course I'm increasing, leveling off here. Again, if you're not sure, just plugging in a random x value over here, it will show you that your output, the y value, is way up here. It will be above y equals 1. And so that is your graph. Questions?
So your only asymptotes will always be the points in the domain that it can't be.
The vertical asymptotes.
Yeah, vertical.
Yeah. The horizontal asymptotes, in general, you can cross them, but sometimes you can't. In this case, we couldn't. But it wasn't because we can't cross them, it's because it would mess up all the previous data that came before it. Another way you can check to see if you can cross a horizontal asymptote is to literally try to figure out, can the y value ever be 1? Right? So we know here that y was equal to x squared over x squared minus 4, right? Now, if y equals 1 at some point, I can literally just plug in 1 here. And I could ask the question, is that actually meaningful? Well, if I solve that, I multiply by x squared minus 4. I'd be able to subtract x squared from both sides, and I get minus 4 equals 0, which is absurd. So it means, no, y cannot be 1. I should never touch that line. So there are tons of ways you can do to double check your work here. But just make sure whatever you put on the picture, it does not contradict anything else you do. If you're going to draw something that's going to create an intercept when there shouldn't be an intercept, don't draw it. Just move somewhere else. Right? And you can always be plugging in points into the original. Remember, this guy is what gives you the location of points on the graph. So if you're never actually sure if you should be there, just plug in a number and see where the output is. So those guys are a little more nuanced, the guys with the asymptotes that look like this. And all of them in the second section are like that. And F from the first section is like that. But yeah, I'll leave it to you guys to do those. So I'm not going to put a problem like this on the third test, but it's possible for the final, depending on my need.
Now with fractions.
Yeah, but there's a bit of nuance to drawing these ones, so I'll give you some more time to get those under control. So on test 3, the curve sketching, I'll actually graph a polynomial. Right, so test 3 is like from the top example, B, C, D, G, H, I.
Wait, say that again.
B, C, G, H, I.
GHI, like the insurance company. From the top. Those are examples of the kind of problem that will come on test 3. For the final, anything.
Oh my god.
On test 3, the gonna be the related rates, right?
Jhevon, do you have an idea when will test 3 be?
Oh, I didn't tell you guys?
No.
After Thanksgiving.
Okay.
Yeah.
Great.
So you guys are at the table and they're asking, what are you thankful for?
You're gonna be crying.
Because you're thinking of the...
You're thinking about that test or something.
No, I already used a meme like that for what day did I do that? For like a Halloween party. Yeah, I can't reuse the joke.
For the last test. You don't mean to me.
Thanksgiving
It's like a de-stress. When you're at the home.
Instead of guessing what meme I'm going to put on, guess what kind of problems I'm going to put on. Some really mean, nasty ones. Okay, never mind. Okay, that's that. I'm kind of getting bored of this. Now, so practice the rest on your own. And again, you can use graph.tk to check your answers. Wolfram Alpha can also do them, but sometimes it zooms out too far. But with graph.tk, you'll be able to zoom and reorient the picture to get a nice idea of what's going on. So yeah, with that, we are moving on to 4.6. Yay! Everyone has a handout. So again, in this kind of problem, in a final, it will come up in part 2, where you can choose to do it or not. The problems will always be word problems, but again, similar to related rates, we always do the same sequence of steps in the same order. Okay, so let's just talk about this. Optimization. Now, this, if for some of you who are wondering, you know, who uses calculus in real life? This is one of the biggest uses of calculus in real life. Right? Optimization, right? Optimizing something, making it the best possible situation, the best case scenario, trying to find that so you know what to aim for. That is called optimization. Now it turns out in real life, a lot of these problems of optimization, you can kind of rephrase it to be in terms of making something as big as possible or as small as possible, right? So if you're a business, what's your optimal situation? Profit as large as possible, right? Costs as small as possible. You know, there are ways you can know what you want to make big and what you want to make small. And once you can rephrase a problem like that, you can use optimization, right? Because as big as possible means maximum. As small as possible means minimum. And we know how to find maximums and minimums now, right? So that's where calculus is going to come in. Once we can find a function to track something we care about, and we know if we want to make it as large as possible or as small as possible, we can use calculus to get to it. Now, another thing in real life is that there are always constraints. You never have an infinite amount of resources. So sure, you want to make your profits as large as possible, but you can only hire so many people to work for you. You can only pay so many people. You only have this many resources. You can, right? There's always a restriction, some kind of limit that hinders you, right? So also to take into account when making something as large or as small as possible, you have to take into account how much resources do we actually have, right? That is called a constraint, right? So, and the thing you want to make as large as possible is called your objective, right? So we're going to use these two phrases all the time, right? So optimization comes from when you want to make something as big as possible or as small as possible to obtain the ideal situation under some constraint. Okay, so that's kind of the background of what's going on. So now let's look at the steps. So step 1, again, it's going to be a word problem. Read it very carefully, make sure you understand what's going on. Okay. 2, draw a diagram. Diagrams are going to come in handy here again. So you're going to read the problem very carefully, understand what's going on. You're going to draw a diagram to represent this situation, right? You're going to set up your constraint and objective equations, right? So now remember, and I said it here, right? The constraint equation is the equation that describes what your restrictions are, what is limited, what you don't have an infinite amount of, right? The objective is the thing you want to maximize or minimize, right? So you're going to set up equations that describe those two things. The 4th step, you are going to solve for one of the variables in your constraint and you're going to plug it into the objective equation, right? You always do that. You do that to get the equation into one variable so you can start taking derivatives, okay? Now in problem 5, in part 5, you're going to now find the maximum and minimum of that function. Maximum or minimum, depending on what you want to use. In general, you want the absolute maximum or minimum, the best possible case, but usually it will be the local max that solves the problem, right? Because the endpoints won't make sense, or they just won't make sense usually. And we'll see why. And problem 6 is to actually answer the question, answer the problem, right? So at the end, there's going to be one final sentence that asks you for something specific, right? You must make sure that you give them that specific thing, right? So that's kind of the idea. Always those 5 steps, always those 6 steps, always in that order. And we're going to do that. So in problem 5, in step 5 is the first derivative test again, right? So that's what we're going to do. To figure out where our max and mins are. Okay. So the bowl is kind of the things that you want to remember, but I suggest you read through everything I have here very carefully. And yeah. Now on the next page we have our examples. All right. So now I'm going to go through these steps that I mentioned very carefully and slowly with problem 1, which is a relatively easy optimization problem. We'll see. And then we'll move on to other ones. And you'll notice here that some of these I actually took from finals, so they are a pretty good representation of something that might come on a test. Okay. So, example 1 from the handout. So we're going to read the problem very carefully. A farmer has 100 feet of fencing and he wishes to make a rectangular enclosure. If he wants to enclose the enclosure to encompass the maximum possible area so that he can plant the maximum number of crops, what should the dimensions of the enclosure be? Right, so here's a problem, right? This guy has 100 feet of fencing, not an infinite amount of fencing, by the way. And he wants to just build a rectangular fence, right? Now the thing is, there are many ways you can build a rectangular fence with 100 feet of fencing, right? You can make it 25, 25, 25, 25, right? Or I could make something like 40, 40, 10, 10, right? Or I could make something like 30, 30, 20, 20, right? There are many possible cases, right? He wants the best one. Which one is the biggest one? Which one will allow him to plant the most crops, right? So that's his problem. He wants to make sure that he can plant the most crops as possible under the restriction that the perimeter has to be 100, right? So this is his problem, right? So now he goes to you, the mathematician, the amazing genius in town. He's like, help me out. I have 100 feet of fence. I want to build a rectangular enclosure. What's the best rectangular enclosure, right? You need to tell him which one of these fences to be, or maybe it's not one of these. Maybe it's something else, right? That is our problem now, okay? So, in order to solve that problem, we are going to go through those 6 steps, okay? So 1, we are going to read the problem. Right? Some things I want you to notice while reading is notice that we have 100 feet of fencing. Right? Which means it's specifically given. Notice that anything actually given is a constraint. It's a restriction. Right, so once they give you a number for something, they say the amount of fencing is this number. Once they give you that number, that's describing a constraint, right? That's what you need to figure out. Like, that's how much fence we have. We don't have as much as you want. We have 100 feet, right? It has to be 100 feet. No more, no less. It's 100 feet that I want to use to get the best possible scenario. That is a restriction. He doesn't have all the fencing he wants. He only has 100 feet, so that's your constraint. Another thing I want you to notice is what he wants to make as large as possible, right? Wants maximum area, right? So in this case, we want to maximize something. That guy is the objective. The objective is to maximize the area, right? Another thing I want you to notice here is what you are asked for, right? You're asked for dimensions, right? So if at the end of the day you tell me, oh, this is the area, you did not answer the problem. I didn't ask you for the area. I asked you for the dimensions, which means I want you to tell me the length and the width of the fence, right? If you tell me anything else, you did not answer the problem. So when you read, those are the things you want to pick out. You want to figure out who's the constraint, who's the objective, and what exactly should the answer be. What do you need me to tell you? Right? So those are the things that when you read the problem carefully, those are the 3 things you're looking for. Okay. So now step 2. Draw a diagram that represents this situation. Now in the problem it says it's a rectangular enclosure. We have a rectangle. So I'm just going to draw a rectangle. Now at this point I do not know anything about the rectangle. I don't know the length, I don't know the width. Those were not given to me. So they're both variables. So let me call the width x and the length y. Right? Now, of course, this has to also be x and that has to also be y because it's a rectangle. But that's my picture. Okay. So step 2 is the diagram. That represents my situation. So step 1, I read the problem very carefully. I am reading to get 3 pieces of information. What is my restriction? What is my objective? What do I want to make large as possible or small as possible? And what should the answer look like? Okay, step 2, draw a picture to describe the situation. Okay, now step 3, I'm going to be setting up 2 equations. I want to set up my objective equation and my constraint equation. Now the objective describes the thing you want to maximize or minimize. In this case, I want to maximize the area. Okay, so my objective equation is going to be an equation that describes area. Because that's the objective. So suppose A is the area. How can I write that as an equation based on the picture that I just drew?
X times height.
X times y, length times width. Okay, constraint. This must describe, I figured out my restriction, the amount of fencing. Right? Which basically here is just going to be the distance around, that's the perimeter. So what's going to be an equation that describes that? Right, I'm going to add up all the lengths of the sides. X plus y plus y. 2x plus 2y equals 100, right? I don't have as much as I want. I only have 100, right? So this equation is called my objective equation. It describes the thing I want to maximize or minimize. This equation is called the constraint equation. It describes my restriction, right? So here I have a perimeter restriction. Okay. So now we move on to step 4. Not yet, not yet. In step 4, we are going to solve for one variable in the constraint and plug it into the objective. You always solve from the constraint, plug it into the objective. So here notice that this is x plus y equals 50, which means that x is 50 minus y, and I'm going to take that and plug it in for the x here. So from the constraint, I know that my x is equal to 50 minus y. This means that my area is 50 minus y times y. Right? I just replace the x with that expression. It's already there. So now what you realize is that I have a function that describes area in terms of the length of one of the sides of the fence. So my area is 50y minus y squared. Now I want to make sure, I want to make this function a maximum, right? So 5, how do I figure out where the maximum point here is? Derivative, we're going to find the critical points.
50 minus 2y.
By the way, notice here that I could have used the vertex formula. I don't actually need calculus, but I'm going to do it the calculus way. In case you don't get a quadratic, you have to know how to do it, right? But I'll still get the vertex anyway, because it happens to be a problem. Okay, so I'm going to find the critical point, which means I'm going to take the derivative of a. I'm going to set it equal to 0 or undefined. It's never undefined. And so what I'm going to have is y must be 25. That's the primitive. Notice when I did here, I only got one answer. Odds are that's going to be the answer I want, right? Because the endpoints don't make sense. When you think of what is the endpoint for a problem like this, how much fencing could I possibly allocate to y on the extreme? Well, I could decide to allocate no fencing to y. But y equals 0 doesn't make sense. I wouldn't have a rectangle. Or the other extremes, I could take all 100 feet of fencing and put it in the y, but then I wouldn't get a rectangle either. So the endpoints 0 and 100 do not make sense, right? So I only got one answer from problem 5. That's going to be the answer I want. But I could test it just to make sure. In this case, I would think of it as an optional thing. So if you're suspicious and you're like freaking out, you know, you put a 25 here and then you plug in random numbers, right? So I plug in like a 1, plug in like a 26, and I plug it into the derivative, which is here. Notice that if I plug in 1 here, I get 50 minus 2, which is positive. If I plug in a 26, I get 50 minus 2 times 26, that's negative. So notice that I'm increasing here, I'm decreasing here, so this is a maximum, and that's what I want. But to me, it's optional. There's only one answer. It has to be that guy.
So if there's two answers, we have to do the...
Right, so if there are two, in the case where there are two answers, then you'd have to check. Unless one of the answers just don't make sense, right? Like if here you get a positive and a negative, there's no way it could be the negative one. You can't have a negative amount of fence, so you just pick the positive. But if there were two positive numbers here, you'd have to do this test to know which one is actually the maximum, which one is the minimum. Right? So for example, if this was a cubic, it's possible to get two possible answers here, and then I'd have to figure out who I should pick. But in general, if you only get one answer and there's no other option, that's the guy, right? I wouldn't even waste time testing. I just say, y has to be 25. So now that brings us to step 6. Now in step 6, I have to remember, what was I asked for? In step 6, I want the dimensions. Which means I want to figure out what is the length of x, what is the length of y. Now if y is equal to 25, this means that my x value is actually, remember it was 50 minus y.
Okay.
So it's 50 minus 25. So this means my x must also be 25, which means the length is 25 and the width is 25. So it's actually the best possible rectangular enclosure is actually a square. A 25 by 25 foot fence will have the largest possible area. And so that's the answer. All right? Now, it could be the case that the problem asks, for example, what is the biggest area? In which case, I didn't really need to find the x. I could have realized that, oh, this is my area formula. Once I find the y, I just plug it in here, and that's the answer. Right? But because I was asked for the dimensions, I had to figure out the x, and that's why the step 6 looks like this. Right? So you always have to pay attention to what it is I'm trying to find. Any questions? It's what?
What is the
It's crazy, everything
vertex
goes
of-
together.
Oh, that's a quadratic. So I know that it's an upside down quadratic. So the maximum would be here, which is the vertex. And I know that the vertex comes from minus b over 2a.
Oh.
So in this case, the b is the 50. So it's minus 50 divided by 2 times a, which is the coefficient of the square, which is minus 1, and I get 25. Any other questions? Okay. We will stop there. We'll pick up with some more examples next time. Do some more of these. But that's a good example to actually go through and see all the steps at play. And we'll pick up with those next time. The homework is already posted for the max and min values and stuff, and this is the following week. And this is the last topic for the test. So once we finish this, you can start the review for the third test. So we will finish this on Monday.
What's the first topic for the test?
I think it was exponential growth in the case.
Okay, I'm not really sure.
Okay. Yeah. It's in the syllabus.